We'll continue our discussion on factoring by talking about some special formulas that really give us some shortcuts when we're looking at specifically trinomials and even a few binomials. Okay, a couple of these formulas we've already really talked about when we dealt with the special formulas for multiplication. We talked about the idea that if you have a binomial squared, that is equal to a trinomial where the first and last terms are squares, and specifically the squares of the two terms in the binomial, and the middle term is double their product. Same thing with the difference squared. If you have a difference raised to a second power, then the expanded form or the multiplied form is the two squares of the terms on the ends with double the product in the middle again, this time with a subtraction in the middle. Okay. And then we also talked about this idea of conjugates. When you multiply two conjugates together where the terms are the same but the sign is different in the middle, they end up being a difference of two squares. So the middle term here would drop out, and you're left with just the a squared minus the b squared, the two terms squared with a subtraction in between. Okay, so we've talked about those three formulas. Now we're going to basically use them in reverse. We're going to start with the answer, the multiplied form, and we're going to break it apart into its factored form. Okay, so let's start with this first one here, the sum squared. Okay, when we were multiplying, I called it a sum squared, but now when we're factoring, we're looking at the other side. We're looking at this trinomial. It's going to have three terms. And because it can be broken down into a perfect square, we call it a perfect square trinomial. In fact, both of these, when factoring, we would consider anything in one of these two forms of the sum or the difference to be a perfect square trinomial. Okay? So perfect square trinomials are polynomials like x squared plus 6x plus 9. A great example of a perfect square trinomial. Again, it fits this first formula because it has a square and a square on each end, right? An x squared and a 9, which is 3 squared. And then if you think about those square roots, the x and the 3, if you double their product, you would get 6x. That's what you have in the middle, which is what you would need to be a perfect square trinomial. As soon as we recognize that, we can then factor this down into x plus 3, the two square roots, the two things that those squares came from, all squared. Okay, so it's essentially x plus 3 times x plus 3. And if you were to expand x plus 3 times x plus 3, you would get x squared plus 6x plus 9, right? The two 3's add up in the middle and they multiply on the end. You could also think of this, we talked about the when we factored in a previous video, when the leading coefficient is 1, you're looking for factors of 9 that add up to 6, okay? And we know factors of 9 that add up to 6 are 3 and 3, and so you could factor it into just x plus 3 times x plus 3, or we could just use this simplified form with the x plus 3 squared. I actually would give you full credit for either of these, x plus 3 squared or x plus 3 times x plus 3. My math lab may want a particular one, and so you want to just clearly read the instructions to make sure you know which answer to input. It may actually accept both. Okay, so that's a sum squared. We can also look at difference squared. Okay, and a difference squared. So a difference squared comes from a perfect square trinomial with a subtraction in the middle. Okay, but always the first and last terms are going to be positive in these. So you could have something like, I don't know, let's go with 4x squared minus, let's do 40x plus 25. Okay. So this may not be as obvious right away that it's a perfect square trinomial, but it is, because this first term is really 2x all raised to the second power, or all squared, right? So this is 2x squared. This here is 5 squared. Whatever we're squaring in each term, if you multiply them together, and I think I did do that wrong. Shoot. That should have been a 20, otherwise this won't work out. Yeah, I need that to be a 20. So if you take the two terms in the middle, the two terms on the ends, multiply them together and double it, you should get the term in the middle. And in this case, 2x times 5 is 10x. When you double it, you get 20x, okay? In my head, when I wrote the problem, I doubled it twice for whatever reason. So anyway, you have to have the minus 20 there. This one will factor then into the first term, the square root of the first term, minus the 5, the square root of that. So it's 2x minus 5, all raised to the second power, okay? Again, you're just trying to recognize that the middle term is double the product of the square roots of the other two terms, okay? So here's a 2, here's a 5, you double the 2 and the 5, you get 20, okay? Or you multiply them and double it. Okay, so some of these are a little bit more basic. They work really nice when the lead coefficient is 1. I think you can see pretty well, as long as this is a square and that's double the square root, it will be fairly obvious. When the lead coefficient is not 1, it's a little bit harder to pick out that this middle term is double the product of the square roots, but it can still be done. And probably is still faster than trying to go through this using the AC method or the modified AC method that we've talked about in previous videos, okay? Although that is an alternative. You could work this problem through using the AC or modified AC method. However, recognizing this formula will allow you to take a shortcut, essentially. It's a little bit less work. Okay, now let's take a look at this last example here where we have a conjugate multiplied together to give us what we call a difference of squares. Well, in factoring, if we start with the difference of squares, we can break it apart into its two conjugates. A real basic example of that might be something like x squared minus 16. It's a difference of two squares. It's pretty clearly two squares. And then you can break them apart into the conjugates. And the conjugates, one will have a plus, one will have a minus. It does not matter the order. And then the terms on either side of those pluses and minuses will be the square roots of these two terms. So you'll have an x in the first spot, and you'll have 4 in the second spot, okay? This one, that formula makes it look fairly simple, I think. Another way to look at this is thinking of this actually as a trinomial. Even though it's two terms, it's a binomial. If you consider for a moment, make a little more room. If you were to consider that this polynomial is the same as x squared plus 0x minus 16. These two things are the same because 0x doesn't really add anything. If I were to try to factor this using techniques that we've learned in the past for trinomials, we would look at factors of negative 16 that add up to 0. Right? So you take negative 16, factors that add up to 0. Well, we have negative 1 and 16, or 1 and negative 16, negative 2 and 8, or 2 and negative 8, negative 4 and 4. And those are all the possible combinations. Well, obviously, negative 4 and 4 are the only ones that add up to 0 in the middle. And so that's where we get the x plus 4 and x minus 4 from. Okay? Okay, so that's another way to look at it. But it also sheds some light on another question that I often get asked by students, and that is, what happens when you try to factor a sum of squares? Right, so if I had another example where I had something like x squared plus 49, those are both squares. What happens? How do I solve that? How do I factor that? And this one's kind of a weird situation, but I can mimic it with this idea of a 0 in the middle. Simply taking x squared plus 0x plus 49. So the question I would respond with is, what factors of 49 add up to 0? Okay, and so we look at 49, well, the factors are 1 and 49, and 7 and 7, and that's it. Well, when you add those together, well, of course you could throw negatives on those, right? You could also have -1, -49, and you could have -7, -7. But when you add those up, each pair, none of them add up to 0, right? The first pair adds up to 50, this one's 14, this one's -50, and this one's -14. None of those add up to 0. And because none of them add up to 0, we get what's called a prime polynomial. We've talked about primes in a previous video as well. So this is prime. Okay? And so what we established, and we can repeat this process no matter what the two n terms are, as long as they're both squares with a plus in the middle, you'll never find factors of the constant that will add up to that 0 in the middle. And this will work for any sum with an exception I'll explain in just a moment. So I would say that as a fourth formula here, the sum of two squares is prime, except, and now I'll give you the exception, except when there's a greatest common factor present. Except when there is a GCF. An example, and these are a little bit more rare, but just to be mathematically correct, I should point it out. An example of one of those might be something like 36x squared plus 9, for instance. Okay. Well, here I have a common. Before I go to the common factor thing, these are both squares. They're both perfect squares, and there's a plus in between, so it actually fits this formula of a sum of squares. However, initially I would think it's prime, except that there's a common factor of 9. And so if I pull out that common factor of 9, I'm left with 4x squared plus 1. And all of a sudden I have a factored form. I have a monomial times a binomial. The original is not actually prime. It does factor into a GCF times a binomial. Okay. Now this binomial is prime from here on out, but that's okay. We want to get this down to prime factors. And so we would not call the original prime. We would say it factors into these two. Okay. So that is an exception. It's kind of rare because you have to have two squares that also share a square factor in order for that exception to occur. 36 and 9 will work. 16 and 4, 36 and 4, 64 and 16, 64 and 4. There's a lot of perfect squares where that does work out, pairs of perfect squares. But at this point, that's going to be the exception. It's pretty rare. All right, so there are two other formulas that we're going to deal with, and they get into cubes, okay, and I'll discuss those in the next video.